Okay, class, this is your ever-loving chemistry teacher, your favorite chemistry teacher, I'm sure. I'm going to talk you through this practice packet here that I've set up for practicing kinetic molecular theory. And so as I work my way through this, you can be accumulating your questions you could ask me later in class. So let's go ahead and get started. Now, I want you to think about some of these points here. What is average kinetic energy? The average kinetic energy of water molecules. Okay, kinetic energy, of course, is energy of motion. Average means that some of the particles are moving really fast and some are moving slow, but there is an average speed. I really hate this question because the answer is a little ambiguous. First of all, you can eliminate water at 90 degrees C has obviously slower motion than 100, and of course ice is very cold, low kinetic energy. But the problem it would be these two here. If it's at 100 degrees C and 100 degrees C, and in fact that means they have the same average kinetic energy, even though one is steam and one is water. So this one unfortunately could have two answers. I won't put it on the test like this, but if you change the question to say the total energy, the steam would have more, because it also has something called potential energy in addition to kinetic energy. So the answer here is either A or C. Boy, that looked bad. Let me rewrite that. So the answer could have been A or C for this first one. Sorry about the confusion. Okay, number 2. Which are the first particles to evaporate from a liquid? Well, you can imagine the ones that are going to evaporate the fastest are the ones that have a lot of speed. And so the ones with the highest kinetic energy tend to evaporate the first. And that leaves everything behind cooler. That's why evaporation cools things. So particles with the highest kinetic energy are surely the ones that will leave the first. Which of the following will evaporate the fastest? So think about it. The more temperature, the more speed of the molecules. So water at 40 degrees C will have a lot more kinetic energy, will evaporate a lot faster than water at 20 or 0. What is the pressure of a liquid when it's at its normal boiling point? Okay, now anytime you see the word normal as a normal boiling point, you have to remember that's 1 atmosphere. And so of these 4 pressures, 1 to 1.3 kPa qualifies as 1 atmosphere. So that's the answer to that one. All right. Going up a little further, water could be made to boil at 105 degrees C instead of 100. The only way you could do that, now remember, just to remind you about boiling here, if I were to draw a picture. So if you have liquid here, there's always a vapor pressure coming off the liquid. However, if above the liquid you have air pressure, which is quite strong, like this, the air pressure pushes down strongly on the liquid, and then the liquid, let's go back to my green here, the liquid has to push up against the air pressure at the same amount. When this pressure, the pressure inside the liquid, equals air pressure, that's when boiling actually takes place. So the answer here, the escape of molecules from the surface of liquid, is known as, oh, hang on a second, we're up here. Water could be made to boil at 105. So the way you'd have to do is you'd have to increase the pressure on the system beyond normal air pressure. You'd have to compress it down. Okay, so the answer would be increasing the external pressure. That would certainly allow the water to get hotter before it starts to boil. Now here, the escape of molecules from the surface of a liquid, that's known as evaporation. Obviously, when it happens at 100 degrees C for water, that's called boiling. But things evaporate at practically any temperatures. Boiling is very specific to the fact you have to have the vapor pressure of the liquid equal to external air pressure. Okay, so now, vapor pressure versus temperature for water. So as you can see from this little graph here, it's showing that water, as it gets hotter, gives off more pressure. So like if you were to draw a picture of a cup, and of course let's put some nice blue water in there. As it's at 0 degrees C, there's practically no vapor above it all, very little vapor. And as you increase the temperature, you can imagine the molecules moving faster, faster, faster. So you end up getting more and more and more and more and more and more particles up here, which is what they call the vapor pressure. The vapor pressure really amounts to the number of particles above there and how fast they're hitting the walls and causing pressure. Okay, so as the temperature goes up, 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 the pressure of the vapor inside there goes up too. Now, one thing about this is millimeters of mercury, so just for the fact that you should know, when it gets to 760 millimeters of mercury, that's equal to 1 atmosphere. So that's why it's showing water at 100 degrees C, the vapor pressure is 1 atmosphere here. Alright, so the question here, what is the vapor pressure of water at 110 degrees C? Okay, so then at 110 degrees C, the vapor pressure, whoa, it's way up there above 1,000. So the answer has to be D. Okay, so let's move on. The normal boiling points of several substances. Okay, so now what that means is that this substance right here boils very cold at 46 degrees C, even while water, you see, boils extremely hot. The main difference is that between the molecules of water, there's a tremendous force of attraction. I'm drawing a heart there to show you how much attraction. Whereas, on the other hand, between these particles, there's a very little attraction, very small hearts here of attraction. So, and as you go down, notice there you have to get them hotter and hotter before they boil. The attraction is increasing. So which of these has the strongest forces of attraction? They would be the ones that boil at the hottest temperatures, in this case water. Alright, so the vapor pressure and boiling. Here we have 4 liquids. Each of them have their own separate vapor pressure at various temperatures. Ethanoic acid, which is, by the way, vinegar. Vinegar will boil, if it's pure, at a much higher temperature than water will. The 101.3 kPa they're showing you here, remember that's 1 atmosphere, so that's the normal boiling point of all 4 of these. So at this point right here, and this point right here, and this point right here, and this point right here are the normal boiling points of these liquids. So, what is the boiling point of ethanoic acid at about 1/2 of normal atmospheric pressure? Alright, so let me get my line in here. 101 is about 1 atmosphere, so about half of that would be about 50, right about here. If you take this line over, right about like that, where these cross, this yellow line is their boiling point at about 1/2 of an atmosphere. Okay, so ethanoic acid, we're talking about this point right here, which is about 100 degrees. Oh, hang on a second. What's the boiling point of ethanoic acid? About 1/2 normal atmosphere. To me, it's about 100 degrees C. Now maybe I've got this picture a little bit wrong. But the closest one here clearly is 80. I might have said even 90, so I'm going to question that answer. But you can see it's about 80, 90. Okay, convert 2.2 atmospheres into kilopascals. So this little conversion factor is telling you that if you have 2.27 ATMs, okay, then we're going to use our little conversion thing here. You take 1 atmosphere is equal to 101 kPa. Alright, so clearly, if you take 2.27 and multiply it by 100, it's going to be, we have to move this over to about 227. Let's see, 2.27 times 100, so it's a little bit more than 227. It must be about this 229, I can't imagine. If you multiply 2.27 times 100, it's 227 plus a little bit. Yeah, it should be 229 kPa. Okay, so the boiling point is the opposite. What is the opposite of boiling point? So remember, boiling is when it's vaporizing. It's going from a liquid to a gas quickly at the boiling point. The opposite process is called condensation. Okay, just like that. So now we're looking at this graph here. The substance shown in this graph is maintained at a pressure of 30 kPa. What phase change can never take place at 30 kPa? Okay, so let's look at this again. I'm going to pull up my line graph here and try to find 30 kPa. It's right about here. So I guess I put a yellow line right about where we're talking at. The question then is, what can never happen at 30 kPa? Okay, so now I see the answer. The answer is that you can get melting, you can get freezing, you can get vaporization, and you can get condensation, either of these four, but you can never get sublimation and you can never get deposition because you have to get the pressure way lower. You see, it's not low enough to cross this line down here. So sublimation deposition can never take place at that pressure for this particular substance. Okay, come on back here. What is the boiling point of the substance shown in the graph when the external pressure is 5 kPa? So shown in the graph when the external is 5 kPa. Uh-oh, we got to go back to the picture. Same picture, I hope? Yeah. So at 5 kPa, it's way down here, 5 kPa, that's very close to the triple point. The boiling point is going to be really cold at 5 kPa. So which one would look best? At 5 kPa, yeah, choices are -5, -10, 10, and 40. Man, I'm going to blow this up big so I can really get a look at it here. Alright, so then I'm going to get my line in. Let's make the line red. So there's 15, 10, 5 kPa. If I bring it right over, actually, at 5 kPa, it looks like it's crossing at about -10. Notice that? Indeed. So there's going to be our answer. The answer is, if you look really carefully at that graph, it's going to be at -10. And that's a tricky one because -5, you know, you might want to guess it's -5, but no, it looks like -10. Okay. Here we have another picture, and so what this is showing is the solid melting. Here's the solid warming up, right here along A. Here it's melting. Here it's heating up a liquid. Here it's boiling, and here you're heating a gas. So at point A, you're really heating a solid. So you're not melting it yet, heating a solid. The answer is C. Okay, so the normal boiling point of several substances. We've seen this graph before already today. Which of these substances would you expect to have the highest vapor pressure at room temperature? Highest vapor pressure means the lowest boiling point. Okay? Because the substance like this at any point has a lot of vapor pressure pushing against atmospheric pressure. So this one has the highest vapor pressure, carbon disulfide. The answer is A. Okay. Okay, moving along. Here we have this next one. The above graph gives the vapor pressure of isopropyl alcohol. Its normal boiling point is, so now normal again, remember that's 1 atmosphere. So 1 atmosphere is 101.3 kPa. So between 75, right in here somewhere, between these two, between 75 and 198, that's 101. So the normal boiling point has to be between 75 and 100. So right there I see the answer to the question is B. Okay, so now we have this material. All right, let's get the question in focus here. All right, so which of these substances has a normal boiling point between 60 and 80 degrees C? Okay, and so normal boiling point has to do with the pressure. So it's in kPa here. It's in kPa, notice. So between 60 and 80 degrees C, we're looking at this set of data right here. And which one of these crosses 101 at that point? And of course this one does right here. It's going from 50 to 108. It's crossing 101.3 kPa. So it can't be this one or this one. The answer has to be ethanol. Very simple. All right, now here we have water or some substance boiling. No, this is probably water here, because over here at 70 degrees C, the air pressure is way stronger than the vapor pressure, so it's not yet boiling. Here it's showing boiling, which means the vapor pressure here of the liquid is equal to air pressure. Notice at 100 degrees C. And here it's actually boiling because the vapor pressure here is way stronger than air pressure. See, the external air pressure is way low here. Say you've gone up on top of a mountain or something, and so the water is boiling at way less temperature. So let's see now. Let's read these illustrations. The vapor pressure of water decreases as you go. No, that has to do with temperature. The kinetic energy of A is higher than B. A is actually lower, see, than B. B is higher at 100 degrees C. The boiling point of water decreases as you go to higher elevations. That one actually looks, that's correct. But let's double check here. The boiling point of water increases as you go higher. No, that's wrong. And the gas is not, no, that's wrong. The answer is C. There you go. That's how you do it. All right, now this picture is explaining what? Why alcohol is a better solvent? No, it has nothing to do with solvents. That means dissolving things. Why vapor pressure occurs, why evaporation occurs even in cold water. Maybe that one. Why cold water has no vapor pressure. That's actually false. And why hot water freezes, that's probably false too. The answer is going to be B. So let me just explain that to you why. So what's going on here is that this curve right here, I'll make it red, is hotter water or hotter liquid of some kind. And this up here is representing colder, because the average kinetic energy here is lower than it is here. The average kinetic energy is much higher. So see, that kinetic energy, remember, is a measurement of temperature. And so when something is cold, even still, there's a large proportion of molecules that are pretty hot, even in cold water, so therefore that's why water will evaporate, even when it's relatively cold. Okay, which of the following statements would be false? Oxygen, hydrogen vapor escapes from water as it is heated. This process increases the temperature, raised. C, oxygen and hydrogen do not escape from water as it's heated. That's completely false. What is escaping is, of course, H2O gas. Indeed, it's not oxygen and hydrogen escaping. Hopefully you don't miss that one. All right, so here we have this question. Which substance would feel colder if placed on your skin? So remember, if you put something on your skin is warm. So let's put some kind of liquid on your skin. All right, Alright, so now your skin is warming up this liquid. The liquid is now evaporating off your skin, which means the highest energy particles are leaving the liquid, like this. So if the higher energy particles leave the liquid, the colder particles are left behind down here, and that sucks the heat out of your skin more and more, which gives you that evaporative cooling. So the question is, which of the liquids has the highest vapor pressure at a specific temperature? And as you can see, A wins by a long shot. A at every point has a higher vapor pressure, you see, than B does. So at the same temperature, let me draw a line to show you here. I'll make a yellow line that's a little bit thicker. So, for example, anywhere you draw a line up like this, B here has a way smaller vapor pressure than does A. Okay, so the question then, getting back to the question, which substance would feel the coldest to place on your skin? Well, it would be substance A, because at every point it has a higher vapor pressure. In the picture above, which statement below is most true? Let's see. So A and B. It looks like B is compressed somehow. Picture A is a solid, picture B is a liquid. No, that, of course, picture A is not a solid. Picture A is a gas, and picture B is a solid. No, I rather doubt that picture B is a solid. Picture A is a gas under high pressure. No, under lower pressure. Picture A is a gas at lower temperature than picture B. They contain the same amount of gas. So no, if picture A is at a lower temperature, then it should actually look, the volume should be smaller. Let's look at, maybe it's this one. Picture A is a gas and picture B is also a gas. Well, that's probably true. Maybe it sounds like a trick question, but no, they're probably both gases, just so this one is under more pressure. So I'm going to guess the answer to that one is C. Okay, so this is a really important picture. This picture is showing the 6 key vocab words. See that? For the different phase changes. You should really understand these. The triple point here is when all 3 phases of matter, solid, liquid, and gas, are together at the same time in equilibrium. So what part of the picture is labeled incorrectly? Okay, now this part of the picture is labeled incorrectly because actually deposition goes this way and sublimation goes this way. The arrows are crossed around the other way. These 4 are correct up here. So the sublimation deposition part is wrong here. Okay, a cylinder with a tightly fitted piston is shown in the diagram below. Air at constant temperature. As the piston moves downward, the number of molecules of air in the cylinder decreases? No, how could it do that? It's sealed up. Increases? No. Remains the same, of course. What a strange question. Okay, so here are which answers correctly the question. So here we have 3 temperature scales. I can tell you right now that A is Celsius, B is Fahrenheit, and C is Kelvin. So A is, which one would that be? A is Celsius, C is Kelvin, and B is Fahrenheit. Looks like the answer is D. Okay, this one here is showing 4 liquids at different temperatures. This one here is the hottest, and this one is the coldest. The highest temperature is A. Easy. Next one. Alright, here's one of those diagrams showing solid, liquid, and gas. The substance shown above is normally. So normal is about room temperature and 1 atmosphere. So you're looking at those conditions. So wondering if the normal temperature in this case is way down here somewhere. And normal pressure is right here. So as you go across and look, it appears like it's solidly in the solid phase. So this substance is normally a solid. Put the point where it's normal is about right there, which is clearly in the solid phase. See, here's where the lines differ. This is the liquid phase. Gas is over here in this area like this. It's kind of like divides it up into a fork. Okay, so here we have 3 temperature scales, water boiling at sea level. So that would mean Celsius is going to be 100, Kelvin is going to be 393. Did I say that right? No, it's 373. And Fahrenheit was going to be 212 by definition. So the Fahrenheit scale should be 212. All right. The average kinetic energy of the gas molecules in container A, B, C, D, so forth. So remember, that's the measurement of temperature. Well, look at this. They're all the same temperature. Oh, cool. That must be, it's the same in all containers. That's right. Now we're getting to the end of the test. So here we have to label things. No sweat. When is it a solid? It's a solid down in G. When is it a liquid? When it's at D. When is it a gas? When it's at C. So solid, liquid, and gas. Very good. When is it boiling? It's boiling when it's at A. And it's condensing when it's going in the opposite direction. You see B, that's condensing. Melting would be when it's going in the direction of E. Freezing would be when it's going in the direction of F. And the boiling point, of course, is H. And the melting point is this letter right there. Looks like a H-I. That's probably I. Or maybe L or I. Okay. And this is the last question of the test. No, 2 more questions. Label the picture above, gas, liquid, and solid. Okay, so clearly that's a solid. This is a gas, and that's a liquid. Pretty easy, huh? You can tell by the maintaining the shape of the container. Solids do not take the shape of the container. And of course the gas is filling the container completely, but liquid doesn't. Okay, then this is the last one on the test. I mean the practice packet here. I said test, but okay. So phase diagram of water. Mark on the graph above where all 3 phases of matter stay in equilibrium. Well, that would be right here at this point. It's called the triple point. Yes, the triple point. Okay, so that wraps it up for your practice. Hopefully you've been able to stay with me through all of this, and hopefully you get a 4 or a nice grade on the next